Welcome to this week's first lecture in EE404. In the last lecture, we have started to investigate the phase-plane trajectories of linear systems. And today we are going to try to present the general case. So let us remember we had a linear system, a second-order linear system, represented by this equation. And of course, we might have some initial conditions here. We would like to draw the phase-plane trajectories for different initial conditions, which means we would like to obtain the phase portrait of the system. We assume that this system, this A matrix here, has two linearly independent eigenvalues, eigenvectors. A has two linearly independent eigenvectors. That is an assumption. In general, we might have the case when A has only a single eigenvector, single linearly independent eigenvector, and we are not going to consider that in this course. It is the advanced linear system theory. So we have two linearly independent eigenvectors. That means that A has the eigenvalue lambda 1 corresponding to the eigenvector E1 and eigenvalue lambda 2 corresponding to the eigenvector E2. We here, of course, assume the second order linear system. That means that X is in R2. So remember what we talked about last time. So if I have my original state space like this, x1, x2, if this is my first eigenvector and this is the second eigenvector E2, then I told you that if I start a system anywhere on these lines corresponding to the eigenvectors, then the system trajectory would remain on that line forever. It might move on that line, but it is going to remain on that line forever. And that actually gives us an idea about how to obtain the trajectories if I start a system somewhere other than on these eigenlines here. So the idea was to define some new state coordinates. The first state coordinate becomes Z1 and the second state coordinate becomes Z2. And then we would like to investigate the trajectory of the system on this new axis. So I can actually take this line and put it into the horizontal axis. That would be Z1, and Z2 would become the vertical axis. And if I can obtain the shape of the trajectories on these new coordinates, then I can quite easily map the same trajectory back onto the original coordinates here. Okay? So now, therefore, the first thing is going to define a new state coordinate change. So a new state via some state coordinate change. So I will define the matrix composed of the eigenvectors in its columns. Okay? I put two eigenvectors side by side and I form the P matrix. Since the eigenvectors are linearly independent, such a P matrix would be invertible. And I will define my new state as follows. So the X is going to be P times Z. What does this mean? This means that X is equal to, I have E1 and E2 times Z1 and Z2. Okay? And if I write this in the long way, this is a matrix vector multiplication. And I know that such a matrix vector multiplication can always be written as Z1 times the first column, E1, plus Z2 times the second column, which is E2. So we see that in this state coordinate change, what we are doing is nothing but we are expressing any state vector x as a linear combination of these eigenvectors. Okay? And the coefficients of those eigenvectors would become my new coordinate variables, my new state vector elements. Okay? So when I take any vector here, x, I am actually expanding it into this. I'm writing it as a linear combination of one vector on the first coordinate axis and another vector on the other coordinate axis. And the first vector is Z1 times E1. This E1 times a scalar, and E2 times another scalar. These these coordinates then would become z1 and z2, and which is my new state vector, which would form my new state vector. And this equation gives us also what z is in terms of x, and it is nothing but P inverse times x. Okay? So now I can obtain the new system dynamics in my new state coordinates. And that is going to be, we have seen in the last lecture that when I obtain the new state dynamics, in that case this new A matrix would be in a very, very simple form. Actually it would be a diagonal matrix, and the diagonal elements would be the eigenvalues of the A matrix. Let us see what we did so far. So I would like to calculate z dot in terms of some matrix times z. Z dot is, using this equation, is nothing but P inverse times x dot, and I have P inverse times x dot is AX, and x is P times Z. P inverse A, P times Z. So we see that this is my new A bar matrix. Okay, that is the new A matrix in the new coordinates. So my dynamics would be looking like this. Okay, and here this A bar is nothing but P inverse AP. But what is this P inverse AP? What would be its form in the general case? Let us try to understand this. So in order to be able to find A bar, what I have to do is to calculate P inverse AP. But we see that here P is in an abstract form. I don't know what E1 and E2 are in the general case, and I have to do such a calculation here in this abstract form. So it is usually not very useful to use this equation in this form. Instead, I am going to convert this equation into the following form. Multiply both sides with P from the left. Okay, then the left hand side is going to be P times A bar. That is equal to A times P. This is going to be the useful form that we can find A bar with this abstract notation, with the eigenvectors as the columns of the P matrix. So I'm going to write this equation in the following form. P is composed of eigenvectors E1 and E2 as its columns. I want to find 2 by 2 A bar matrix here. And I have A, whatever it is, and P is E1 and E2 here. Okay? So when you multiply the A matrix with another matrix composed of these columns, you can write the resulting matrix as follows. You can multiply each of these columns with the matrix A, and you would get the matrix multiplication A times P. Here, this is P, and this is P. So A times P is going to be composed of A times E1, and I have A times E2. Okay? The columns of A times P are nothing but A times the columns of P. Okay? That is some partition matrix rule that you can use. I know that these matrices A times E, these vectors A times E1 and A times E2, they are going to be a constant multiple, eigenvalue times the same eigenvector. So the right hand side here is nothing but lambda 1 times E1, and the second column is going to be lambda 2 times E2. Because E times E1 is lambda 1 times E1, and A times E2 is A times E1 is lambda 1 times E1, and A times E2 is lambda 2 times E2. So you see that the first column of the right hand side is the eigenvalue times its eigenvector, and the second column is eigenvalue times the second eigenvector. Okay? So I have to make sure that this multiplication on the right hand side would also give me the same columns. Okay? Now I have these elements A bar 1 1, A bar 2 1, and I will first consider only these two elements. Okay? How do you obtain the first column of this multiplication, P times A? How would we obtain the first column of the multiplication P times A bar? Okay? What I do is that I will take this column and I would make it horizontal, and I would multiply it with the columns of the matrix P here. Okay? So the first column of this multiplication, P times A bar, would be A11 bar times the first eigenvector plus A21 bar times the second eigenvector. Okay, this is the matrix multiplication rule. How do you obtain the first column of the multiplication of two matrices? You would take the first column of the matrix on the right, and you would make that column horizontal, and you would multiply the first column of the matrix on the left with the first coefficient plus the second element here in this column times the second column of the matrix on the left. Okay? That is again some partition matrix multiplication rule. So if I write here the first column of this multiplication, I would obtain the following. I will erase this. The first column would be A11 bar times E1 plus A21 bar times E2. This would be my first column of this multiplication. And the second column is going to be what? If I put here these elements, A1 2 bar, and I have here A2 2 bar, then that is going to be, the second column is going to be A1 2 bar times E1 plus A2 2 bar times E2. Okay? Then I need to equate these two matrices. Okay? So you see that the first column on the right hand side is nothing but lambda 1 times E1. So how should I choose my A bar here? How should I choose these coefficients such that the first column is nothing but lambda 1 times E1? The selection is obvious. I need to choose A11 bar as lambda 1 and A21 bar as just 0. Okay? In that case, I would make sure that the first column on the left hand side is lambda 1 times E1. Okay? So here we see that our A bar, the first column of A bar is going to be lambda 1 and 0. What about the second column? I will do the same thing. I need the second column to be lambda 2 times E2. So I need to choose the second column of A bar such that this summation is lambda 2 times E2. But that is possible only if I choose A1 2 bar as 0 and A2 2 bar as lambda 2. So the second column of A bar would be this. So you see that I don't know the A matrix, I don't know its eigenvalues, I don't know its eigenvectors, but I can know what P inverse AP is, okay, by using this type of logic. So what we are doing is nothing but multiplying A with the first column of P, and then we are writing that result in terms of the columns of P again, and we are writing the coefficients here into the first column. And then I calculate the second column of A times P, and then I write this second column as a linear combination of the columns of P again, and the coefficients would be the second column of A bar. So now I'm going to actually write the new system. So in that case, Z dot is going to be A bar times this matrix, lambda 1, lambda 2, 0, 0, times Z. Okay? So now I can write the individual dynamics here. The individual dynamics would be the following. Z1 dot. So we see that now the dynamics of the components of Z would be decoupled. In general, A might be filled with non-zero elements. All of the elements can be non-zero. In that case, the dynamics of x1 and x2 would be coupled with each other. But here, by obtaining a diagonal A bar matrix, then we decoupled the dynamics for the elements of Z. And that would give us Z1 dot is equal to lambda 1 Z1, and Z2 dot is equal to lambda 2 times Z2. So you see that these dynamics, these two dynamics are now decoupled. What do I mean by that? Dynamics of Z1, differential equation for Z1 is not dependent on Z2 and vice versa. Okay? But these two equations can be easily solved as follows. Z1 of t is equal to e to the lambda 1 t times the initial condition for Z1, and Z2 of t is equal to e to the lambda 2 t times the initial condition for Z2. Okay? So now we would like to obtain the phase plane trajectory in the Z plane. If I can extract Z2 in terms of Z1 from those two equations, then I can draw the resulting trajectory onto Z1, Z2 plane, and I would obtain the trajectory in Z1, Z2 axis. And then I can try to map it back to the X1, X2 plane. Okay? So here I would like to tell you what happens when one of these initial conditions is equal to 0. Suppose that Z1 0 is equal to 0. In that case, what would happen to Z1? If the initial condition for Z1 is equal to 0, that means that the initial condition is on this Z2 axis. So the Z1 0 is 0. Then what is going to happen? You see that if Z1 0, the initial condition for Z1 is 0, then Z1 of t is going to be 0 for all time. Because if you choose this Z1 0 as 0, then Z1 of t is going to be 0 for all time. Okay? That means that if I start the system on the vertical axis here, as by choosing my initial condition as such, then the system trajectory is going to remain on this axis forever. This is similar to the behavior of the system on the second line corresponding to the second eigenvector. Remember, these axes are nothing but the eigenlines. So the behavior of the system on these lines, it is copied into these new axes. Okay? So if I start the system here, that means that my initial condition for Z1 is 0. That means that Z1 is going to be equal to 0 forever. Okay? The system trajectory might move on this line, but it's never going to be able to leave this line, similar to the second eigenvector case here. And I have the other behavior. If I choose the initial condition for Z2 equals to 0, then the system trajectory will never be able to leave the Z1 axis here. All right? So now I'm going to try to extract the trajectories formula for the Z1, Z2 axis. In order to be able to do that, I will try to cancel time from these equations. I will try to write Z2 in terms of only Z1, and I will try to get rid of the time from both of these equations. So here I can write Z1 over Z1 0 is equal to e to the lambda 1t. We have done this in the last lecture for a specific system. Now I'm doing the same thing for the general case. And I would have here Z2 over Z2 0 is equal to e to the lambda 2t. Okay? Now you see that this is going to be always positive because exponential is always positive. Similarly, this is always positive. I can take any power of both ends sides here. I will take the powers. And while doing that, I will try to match the right-hand side of this equation to the right-hand side of this equation. So I will take the lambda 2 power of the both ends sides here, and I will take the lambda 1 power of both sides here. Okay? And you see that the right-hand side here is going to be e to the lambda 1, lambda 2t, and the right-hand side is going to be e to the lambda 1, lambda 2t. So you see that the right-hand sides would become the same when I do this power operation, and then the left-hand side should be the same as well. So I first take the left-hand side here. So z2 over z20 to the power lambda 1 is equal to z1 over z10 to the power lambda 2. Okay? So now I will take the 1 over lambda 1 power of both ends sides. So that is going to give me, so I would have z2 over z20 is equal to z1 over z10 lambda 2 over lambda 1, and if I leave here this z20 alone, then it's going to be z2 equals to, I would have z20 times z. So let me write these coefficients in a good way, in a better way here. So you see that here I have this z20 coming here alone, and I have z10 to the power lambda 2 over lambda 1 times z1 to the power lambda 2 over lambda 1. Okay? So I would have this equation, and you see that this coefficient here is nothing but a combination of the constant initial conditions. They are independent of time. That means that I would get the formula z2 equals to alpha times z1 lambda 2 over lambda 1. Okay? So we get this general formula for the trajectories in the z1, z2 plane. Okay? So we see that the z2 is always going to be some power of z1 times a coefficient alpha. Okay? So we would always have this type of relationship here. And depending on the values of lambda 2 and lambda 1, we are going to have different powers of z1 as z2. Okay? So now let us try to investigate some specific cases. Let us write here types of equilibrium points of linear systems. So when we try to see the specific cases, we are also going to specify the equilibrium points of those linear systems. So the first case is going to be the following. I will have lambda 2, which is greater than lambda 1. Remember here, I have actually forgotten to tell you here. Here I am assuming the real eigenvalue case. Okay? I have forgotten this, sorry for this. It's very important here, because if the eigenvalues were complex, then what would be a problem? So here, in that case, I would have z1 that is equal to a complex number times z1 okay? And in order to be able to draw those trajectories, I want just real variables here. So in this case, I'm assuming that this lambda 1 and lambda 2 are actually real eigenvalue case. So here I have lambda 2 is greater than lambda 1, and let us say that they are both greater than 0. Since the eigenvalues are real, I can write this type of inequalities. If the eigenvalues could be complex, then such an inequality would not mean anything. It would be meaningless. Okay? In that case, what would be our trajectories like? So here, both of these eigenvalues are actually positive, and the second eigenvalue is larger than the first eigenvalue. So we have the following case. Z1 dot is equal to, let us say, 1Z1, and Z2 dot is equal to, I would have in this case 3Z1. I'm making this up. Okay? In this case, where are the equilibrium points of this linear system? In that case, if I equate the right-hand side to 0, then I would have Z1 equals to 0 and Z2 equals to 0 as my equilibrium point. I have a single equilibrium point at the origin. And if you look at the eigenvalues, if you look at the original system, x dot is equal to ax, and if you try to calculate the equilibrium points of that original system, it is also going to be exactly at the origin. Only a single eigenvalue at the origin. Why is that? How can I be sure that that A matrix is going to be invertible actually? So I know that the A matrix is invertible because both of the eigenvalues are non-zero. A matrix is invertible if and only if, let me write here, a matrix A is invertible if and only if lambda I is not equal to 0 for all I. If and only if it doesn't contain any zero eigenvalue. We're going to see why this is the case. And actually here, at the end of the next lecture probably, or the one after that, we are going to see the following fact. Determinant of A is going to be the multiplication of the two eigenvalues of this matrix. So determinant of a matrix is nothing but the multiplication of its eigenvalues. Okay? Since the invertibility of that A matrix corresponds to the case determinant A being non-zero, if both of the eigenvalues are non-zero, determinant is never going to be 0. As a result, for this case, the matrix A is going to be invertible. That means that the only equilibrium point of this original system is going to be at the origin. And in the Z system, in the new coordinates, this equilibrium point is transferred to the equilibrium point at the origin again. Okay? Remember, we have the equality x equals to p times z. That means that if x equals to 0, then z is equal to 0. So the original equilibrium point of the system is transferred into the origin equilibrium point in the new coordinates. Okay? This is always the case because of this relationship and because p is always invertible. Okay? So now I would like to show the trajectory on Z1, Z2 plane, okay? And in this case, I have this, Z2 equals to alpha. I don't care about alpha. This is only determined by the initial conditions. Z1 to the lambda 2 over lambda 1. So for this example, lambda 2 is 3, lambda 1 is 1. So the relationship would be Z2 equals to alpha times Z1 cube. Okay? So I would here draw a curve which would convex upwards like this here. All right? And in the other case, I would show this. And if alpha becomes negative, in that case, I would have this type of trajectories. And I would have here my equilibrium point. And how about the motion on these trajectories? You see that whatever the initial conditions are, they can be positive, negative. If they are not zero, these exponentials, they would be exponentials like e to the t or e to the 3t. So these exponentials would be growing towards infinity on the trajectories. That means that Z1 is going to increase and Z2 is going to increase. So the trajectories would be pointing away from the equilibrium point. Okay? I can here draw other lines corresponding to other initial conditions like this. On all of them, the trajectory directions would be similar. What about the axis here? If I start the system here, then I know that the trajectory would be on this line forever. And in that case, what would happen? If I start the trajectory here, then what does that mean? That means that the initial condition for Z2 is 0. So Z2 is going to be 0 forever. Okay? But Z1 0 is positive, and you see that the trajectory is going to be e to the lambda 1 t times Z1. Lambda 1 is positive. That means that my trajectory would be moving towards the right and diverging towards infinity. So the trajectories on this line are like this, and trajectories on this line are like this, because both of the eigenvalues are positive. Okay? And now what can I say about this equilibrium point? In control theory literature, or nonlinear control, or in nonlinear control theory, if I have an equilibrium point around which the trajectories are in this form, I would call that equilibrium point to be a node. A node type of equilibrium point. If both of the eigenvalues are positive, if they are real and positive, I'm going to call this equilibrium point as a node. And we see that the trajectories around this equilibrium point, they are all diverging away from that equilibrium point. And in that case, we are going to classify this description here with the adjective unstable. Okay? So this equilibrium point is an unstable node. That is a sentence that you can hear in control theory. Similarly, we're going to classify the original equilibrium point of the system here, the original system, as an unstable node. Okay? So we are going to decide on the type of the equilibrium point by looking at the eigenvalues of the A matrix. If they are both real and positive, then that equilibrium point is going to be called an unstable node. If both of the eigenvalues were negative, then the directions of the motion would be changed here, but I might have similar trajectories. In that case, the equilibrium point would be called a stable node. Okay? If both of the eigenvalues are real, and if they have the same sign, then we are going to call the equilibrium point, corresponding equilibrium point, as a node type of equilibrium point, and depending on both of their signs, we would call it either unstable or stable. Okay? So now let me see the other case. What happens if actually lambda 1 is larger than lambda 2? In that case, we will have also trajectories diverging away from the equilibrium point, but in that case, we would have an important change in the shape of the trajectories, and we are going to see that in that case, we would have concave trajectories. So remember our expression. So this is our system dynamic, or the solution of the differential equation, and this is our equations. Z1 to the lambda 1, lambda 2 over lambda 1. Okay. So what happens? The second case is going to be lambda 1 is larger than lambda 2, and they are both larger than 0. In this case, the matrix A and furthermore the matrix A bar, they are both invertible, so the only equilibrium point is the one at the origin. So on the axis, so I have this Z1, Z2. On the axis, the motion here would be the same because both of the eigenvalues are still positive. All right? And then, but the shape of the trajectory is going to change. Here, just as an example, let me say that lambda 1 is going to be 2 and lambda 2 is equal to 1. In that case, my trajectory would be something like this. Z2 is equal to alpha, lambda 2 is 1, lambda 1 is 2, Z1 to the 1 over 2. So you see that in this case, the trajectory on the first quadrant cannot be like an x cube or x square. It cannot be convex in this way. It's going to behave like square root of x, which is going to be in some way convex downwards, or sometimes we call it as a concave curve. Okay? So in that case, our trajectories would be like this. Sorry, I'm really sorry. Okay? So I can actually draw similar curves for different initial conditions here, and that would make this picture as a phase portrait. Okay, so that is our trajectories. That's how they look like, and they are behaving like before. They're diverging away from the equilibrium point. As a result, I would call this equilibrium point an unstable node as well. So here the naming is just like this. If lambda 1 and lambda 2 are both real, and if lambda 1, lambda 2, if they have the same sign, okay, which means that lambda 1 times lambda 2 is strictly greater than 0, that is, I'm assuming them to be non-zero, both, and they have the same sign, then the equilibrium point is going to be called a node. Okay? And depending on whether lambda 1 and lambda 2 are positive or negative, we're going to determine the stability of that equilibrium point. And if the eigenvalues are both negative, then it's going to be a stable node. If they're both positive, then it's going to be an unstable node. So now let us see the other cases. Now maybe I should be faster a little bit. So let us quickly go over the following case. The case 3. Let us say that they are both smaller than 0 in this case, and I would have this inequality. In that case, how would the trajectories look like? So I have Z1, Z2 here, and now I know that both of the eigenvalues are actually negative, okay? If they are both negative, then A matrix is invertible, A bar matrix is invertible, and that means that I have a single equilibrium point at the origin, and similarly for the original system. And what about this case? The trajectories would be concave or convex. So here we see that the first thing that I can do here to mark the arrows onto the axis here, what is going to happen on the axis? I see that now these exponentials are decaying. As a result, if we start the system anywhere on these axes, they're going to travel towards the equilibrium point. Okay? Similarly for the other axis. And what about the convexity, concavity? So the easiest way to decide this is just to give some numbers to. So let me give lambda 2 is equal to -3, or let us say it's -2, and let us say lambda 1 is -1. In this case, the expression would be Z2 is equal to alpha Z1, and that is lambda 2 over lambda 1. It would be just square here, okay? So you see that the trajectories would have would be convex in this case, just as in the first case. And in this case, an important change is that they are converging towards the equilibrium point. Wherever I start the system, the trajectories are ending up at the equilibrium point of the system. This type of equilibrium point is called a stable node. Okay? You see that lambda 1 and lambda 2 are both real and they have the same sign. So this inequality is satisfied. So we have a node and it is stable. Let us see the fourth case. So I would have lambda 1 is smaller than lambda 2, smaller than 0. In that case, just give some numbers and see that the trajectories would be this type. And they would be converging to the equilibrium point. So we have again a stable node. Okay? In all of these cases, the eigenvalues were distinct from each other. None of the eigenvalues were the same. Okay? Now let us consider a fifth case where we have equal eigenvalues. They might be positive or they might be negative. That is determining the stability. So the fifth case is the case when lambda 1 is equal to lambda 2, and let us say they are both positive. Okay? In that case, it is easy to judge the trajectories. Z1 is going to be Z2 is going to be alpha times Z1 to the power 1. Okay? And this alpha can change its value depending on the initial conditions. But Z1, so here I have Z2 is equal to alpha Z1. This is an equation for a line, right? So the trajectories are going to be linear. Linear trajectories like this. And what about convergence or divergence away from the equilibrium point? In this case, we have again a single equilibrium point at the origin. Eigenvalues are both non-zero. And that means that we have a single equilibrium point. And in this case, they would be diverging away from the equilibrium point because of the positive sign of the eigenvalues. And we can quickly see the negative sign. If they are both smaller than 0, then I would have the opposite picture. So similar trajectories like this. And what about the ones on the axis? They would be similar. In this case, the trajectories would be converging towards the equilibrium point. And what about the characterization? We still have a stable node, sorry, in this case, unstable node. And we have a stable node in this case. Okay? So now we have finished the real eigenvalues with the same sign case. And secondly, we are going to see eigenvalues with differing signs. So now let us see the case 7. In this case, let me say that we have the following inequalities. Both of the eigenvalues are real, but we have just different signs for these eigenvalues. Lambda 2 is positive and lambda 1 is negative. In this case, how would we are going to have a significant change in the trajectory characteristics here. In this case, it is almost no change. It's just the convexity or concavity of the trajectories change when they and only the stability changes depending on the sign. So here, the trajectories would be significantly different than these earlier ones. So here, let me first try to look at the invertibility of A. In this case, both of the eigenvalues are still non-zero, and that means that their multiplication, which is the determinant, is going to be non-zero. So A matrix is just going to be invertible, and A bar is going to be invertible. That means that we have only a single equilibrium point at the origin. Okay? So now let us try to decide on the trajectories on these Z1, Z2 axis. So I see that lambda 1 is negative. That means that if I suppose that Z20 is equal to 0, so I choose an initial condition here on the Z1 axis. So Z2 is 0 forever. And what happens to Z1? Z1 is going to have a decaying exponential times a positive initial condition. So we see that the trajectories on this part is going to be converging towards the equilibrium point on the Z1 axis. And what happens if I choose Z10 negative? Z10 negative, but this exponential is always positive and decaying. So that means that we are going to have a trajectory, again converging towards the equilibrium point on the Z1 axis. Okay? So now let us try to look at the motion on the Z2 axis. Suppose I choose the initial condition for Z1 0, and in that case Z1 is going to be 0 forever, and Z2 0 is going to be positive, and in that case lambda 2 is positive. That means the trajectory is on the Z2 axis would be diverging away from the equilibrium point. Okay? Similarly on the other side. So we see that the behavior of the trajectories would change depending on which axis we are talking about. So what happens if I start a system on another point other than on these axes? So again, it's easy to select some values here. Suppose that lambda 1 is -1 and lambda 2 is +1. Okay? Lambda 1 is -1 and lambda 2 is +1. They satisfy these inequalities. In that case, lambda 2 over lambda 1 would be just -1. Okay? And so that is going to tell me that Z2 is going to be alpha times Z1 inverse. So Z2 is going to be like Z2 is alpha over Z1. Okay? So my trajectory would be behaving like X inverse here. So it would be a trajectory like this. Similarly, on other axes, I would have similar behavior here. So here I would have to decide on the directions on these, or for different initial conditions, we would have these type of curves. And here, how should I decide on the directions of motion on those trajectories here? So you see that the Z1 should always decrease in magnitude and Z2 should always increase in magnitude. Okay? If I am on this curve, then Z2 should increase and Z1 should decrease. So you see that the direction of motion should be like this then. So this is a way of thinking. Another way of thinking is more intuitive. Just look at the graphics and you see here that the motion should be like this, like this. Just look at the axis motions here, okay? So the motions on the axis. So the motions on these curves should be fitting the motion on the axis here. So here you see that this trajectory goes like this somehow. So I can make this direction like this, and here the same. Okay? So you can argue with in different ways. So when we have eigenvalues real, and if they have differing signs like this, we call this equilibrium point as a saddle point. Okay? So this is the case when both of the eigenvalues are real, but the lambda 1 and lambda 2, if I multiply them, we are going to get a negative number because they have differing signs. In that case, we are going to call the equilibrium point to be a saddle point. And if I ask you, whether a saddle point is a stable equilibrium point or an unstable equilibrium point. With your intuition, how can you answer such a question? Is that equilibrium point a stable equilibrium point or an unstable equilibrium point? Here is how we decide on that. If all trajectories around an equilibrium point converge back to the equilibrium point, then we call that equilibrium point stable. If at least one type of trajectory diverges away from that equilibrium point, then we would call that equilibrium point an unstable equilibrium point. Okay? So for stability, all trajectories around the equilibrium point should converge. For instability, there should exist at least one trajectory which diverges away from the equilibrium point. Okay? So here, if you look at this equilibrium point and if you look at the trajectories around it, you see that there exist actually trajectories that are diverging away from this equilibrium point. Okay? So that is why if we are asked about the stability of a saddle point, we always say that it's an unstable equilibrium point. Okay? Because there always exists an eigenvalue which is positive, okay, in that case. If I look at the other case of the saddle point, in this case, let us look at the other case. So I have 8 here. In this case, let us say that lambda 2 is negative and lambda 1 is positive. So I will go over quickly here. In this case, A is again invertible, so I have a single equilibrium point at the origin. And the motion on Z1, because lambda 1 is positive, is going to be away from the equilibrium point. Motion on Z2 axis would be converging towards the equilibrium point, and the trajectories would be similar like this. And if I put the directions here using these axes here, I would put them like this. And this is again a saddle point, and of course it's unstable. So now we finished the cases where both of the eigenvalues are non-zero. Now we're going to consider the cases when actually at least one of the eigenvalues is equal to 0. Okay? Let us consider this case. So I would have the case 9 here. Let us say that lambda 1 equals to 0, and let us say that lambda 2 is positive. Or here, I really do not want to deal with positiveness or negativeness. I would like to consider them both. Let us say that lambda 2 is not 0. Okay? It might be positive or negative. It's just going to change the direction of motion. All right? So I have here Z1 and Z2. Now let me look at the Z1 and Z2 system. Z1 dot is equal to lambda 1 is 0, 0 times Z1. So Z1 dot is 0 here completely. Okay? And Z2 dot is equal to lambda 2 times Z2. Okay? This is my decoupled system. Now I want you to find the equilibrium points of this system. So you see here that when I try to equate the right-hand side to 0 here, the right-hand side of the first equation is already 0. It is always 0. So this is not going to bring me any constraint about Z1. Okay? But the second equation is going to bring me the constraint of Z2 being equal to 0. So Z1 can be anything, and Z2 is going to be equal to 0. What do these equations describe to you? So which points on the Z1, Z2 axis those equations would give us? So you see that there is no constraint on Z1, but Z2 should be equal to 0. So we have Z1 axis as our equilibrium points. So we have equilibrium points all over the Z1 axis. These are the equilibrium points in the new coordinates. Where are the equilibrium points of the original coordinates? Z1 corresponds to the first eigenline here, okay? So the equilibrium points of the original system would be on this line, corresponding to the first eigenvector, okay? So we have an equilibrium zone in this case. Not a single equilibrium point at the origin, but we have an equilibrium zone. Okay? All points on the Z1 axis, they are equilibrium points. So if I start the system anywhere on the Z1 axis, the trajectory is going to remain there forever. Nothing will move if I start the system anywhere on the Z1 axis. But if I start the system somewhere outside the Z1 axis, what is going to happen? So we see that from the first equation, wherever I start the system, the Z1 value will not change. Because here we see that Z1 dot is always 0 according to the system equations. Or you can see here, since lambda 1 is equal to 0, Z1 of t is e to the 0, which is 1. Z1 of t is equal to Z1 0 forever. So Z1 is going to be equal to its initial condition forever, and Z2 is going to change. So wherever I start the system, Z1 value would be the same, okay? So the trajectory would always be on such a line, okay? And what about the direction on that line? The direction is going to be determined by the sign of lambda 2. If lambda 2 is negative, then I would have a direction downwards towards the equilibrium zone. So this is the case when lambda 2 is smaller than 0. Or the direction would be away from the equilibrium zone if lambda 2 is positive. Okay? And if I do the same thing I can do the same thing for any other value. So similarly, if the trajectory, I can start with a negative Z2 0. In that case, this direction is going to correspond to lambda 2 smaller than 0, and this direction would correspond to lambda 2 strictly greater than 0. Okay? So similarly, I have these directions on other initial conditions like this. So this is the motion in the new coordinates, in the Z1, Z2 coordinates. How would you expect the motion in the original coordinates? In that case, we would have the equilibrium zone here like this, okay, on the Z1 axis, and the other trajectories would be parallel to the Z2 axis like this, and their direction would actually depend. So just take these Z1 and Z2 axes and take them and put them here. You need to rotate them and you need to move them just a little bit, and then you need to put them here, and then you're going to get the motion in the original coordinates. Okay? So in this case, what is the description or the name of these equilibrium points? In general, we don't give any names to those equilibrium points, okay? So there is no description. There is no specific name like a node or any other name given to these type of equilibrium points in this equilibrium zone, okay? They are non-isolated equilibrium points. There are infinitely many equilibrium points here on this line, and we don't give any of them a specific name. When I draw these trajectories like this, you need to be very, very careful, because this trajectory, if I start it here, it is not actually going to go here in this direction, and then it's going to pass this z1 axis, and it's going to continue to the other way. Okay? Why is that? Because here, when this trajectory comes or reaches to the z1 axis, when it reaches the z1 axis, then it's going to stop there, because there is an equilibrium point there, and as a result, when the trajectory reaches z1 axis, it's going to stop there with whatever the z1 value it reaches. It's not going to continue anymore to the other side. Okay, so when I draw a trajectory like this, it doesn't mean that this trajectory would continue like this, or this trajectory would continue. If we reach this point somehow, then it's going to remain there. Similarly, in the original coordinates, if I start the system here, and if the eigenvalue 2 is negative, the trajectory is going to travel on this line, and it's going to end up here, and it's going to remain there forever. Okay. So we see here that these equilibrium points in the Z system are their number. The number of equilibrium points in the original system is equal to the number of equilibrium points in the Z system here. Why is that? Because that P matrix is always invertible. So if there are infinitely many equilibrium points in the Z system, there will be infinitely many equilibrium points in the original system, in the original coordinates. Okay? So here I can also say the same thing for the A bar and A matrices. If A bar is not invertible, A is not invertible either, or vice versa, because of the P matrix invertibility here. And we have just few cases left. Case 10 is going to be lambda 2 equals to 0 and lambda 1 is not equal to 0. So it is not, I think you have understood, I hope I could make you understand the main idea here. In this case, since lambda 2 is equal to 0, the equilibrium region, equilibrium zone would be on Z2 axis, and the trajectories would be like this. Constant Z1 lines, okay? Sorry, constant Z2 lines, and whether they are diverging or converging would be determined by the sign of lambda 1. This is the case when lambda 1 is smaller than 0. This is the case when lambda 1 is larger than 0. Similar for the other side. And if you look at the motion in the x-coordinates, you would then expect motion on these parallel lines to the z1 axis. And the final case that we can consider is lambda 1 is equal to lambda 2, and they are both equal to 0. In this case, how would you expect the trajectories? So here, you see that if lambda 1 and lambda 2 are both equal to 0, that means that we are going to have equilibrium zones on both Z1 axis and Z2 axis. Okay? But is that all? Since lambda 1 is equal to 0, we are going to have an equilibrium zone on the Z1 axis. Since lambda 2 is equal to 0, we are going to have an equilibrium zone on the Z2 axis. But are these the only equilibrium points? There are infinitely many of them. But are these the only equilibrium points of this system? Here you have to think just a little bit. If lambda 1 is equal to 0, when I start the system at a point, Z1 is not going to change. Okay? Because the equation for Z1 is Z1 dot is equal to lambda 1 times Z1, and lambda 1 is equal to 0. That means Z1 dot is equal to 0. The equation for Z2 is Z2 dot is equal to lambda 2 times Z2, which lambda 2 is 0. So Z2 dot is equal to 0. So that means that wherever I start this system, Z1 and Z2 will not change at all. What does that mean? That means that the whole state space, the whole Z1, Z2 space is filled with equilibrium points for such a system. Okay? So we see that equilibrium zone is nothing but the whole state space R2. Why is that? Because look at the equations. The right-hand sides are both equal to 0, so no constraints on Z1 or Z2 for an equilibrium point. Okay? And here you can also say that, remember the matrix A bar is a diagonal matrix which contains the eigenvalues on the main diagonal. But if both of the eigenvalues are 0, then A bar is going to be equal to the 0 matrix, 0, 2 by 2. But if A bar is equal to 0, because of the invertibility of the P matrices, A should be equal to 0. Okay? That means that A is equal to 0 here, so x star is, the equation is like x star is equal to 0, meaning that the whole state space, x1, x2 space, is filled with equilibrium points for such system. That means that wherever I start this system, in the state space, it's going to remain, the trajectory will be on a single point. Similarly for the system in the original coordinates. So this actually completed our investigation for the linear case and for the real eigenvalue case. So we see similarly for this type of equilibrium zone, we don't have any specific name. So we have seen the real eigenvalue case for the linear systems, second order systems. Now the next thing that we're going to see is going to be the case with complex eigenvalues. Okay? In that case, just as in your control course, complex eigenvalues is going to mean some oscillations in the system. So you see that in the real eigenvalue case, we didn't see any oscillatory motion here. No loops here in the motion. We are only having the diverging or converging behavior depending on the sign of the real eigenvalues. In the complex case, we are going to start seeing some oscillatory motion. So around the equilibrium point, we might have rotations. Sometimes these rotations will converge to the equilibrium point, and sometimes they are going to diverge away from the equilibrium point. Depending on this divergence or convergence, we are going to call the equilibrium points again like unstable or stable. In general, when we look at the oscillations, whether the oscillations are converging or diverging away from the equilibrium point will depend on the sign of the real part of the eigenvalue. Okay? The real part of the eigenvalue will determine whether the oscillations are going to converge to the equilibrium point. If they are negative, then the oscillations would be converging to the equilibrium point. If they're positive, then the oscillations would be diverging away from the equilibrium point. If the real part is 0, then that is going to mean that we are going to have pure oscillations, non-diverging, non-converging oscillations like this. Okay? And the frequency of the oscillations, on the other hand, will be determined by the imaginary part of the eigenvalues. Okay? But we're going to see this type of concepts in the next lecture. That's all for this one. Thank you very much for watching. Bye.